Good evening, everyone. Welcome to this live lecture. Welcome to the fifth week of the live lecture on the Computational Fluid Dynamics course offered in NPTEL by Professor Srinivas Jayanti. I am Sankar H. I am your TA for today. I will be available on Mondays from 6 o'clock to 8 o'clock. I will be conducting this session today. So let's start with what we have here. We are going to do the graded assignments for week 4, the non-graded assignments for week 5, and the graded assignments for week 5. As we have already crossed the deadline for all of these assignments, and we are still yet to discuss everything in detail together. So we'll go slowly discussing each and every problem to go through it. Week 4 was dealt with reaction mechanisms and CFD for when there is a reaction and flow reactor or something of that sort is what we did in week 4. We'll start with the question. A catalytic flow reactor having dimensions of L times W times H such that the length in the Z direction is much greater than in the other two directions. Okay. L is much greater than W and W is much greater than H. Gaseous mixture of CO and H2O enter the reactor through plane A and leaves through plane D. This is the image that's shown. So let's assume that this is L and this is H. So this should be L and this should be W and that should be H. A gaseous mixture of CO and H2O enters through plane A and leaves through plane D. So this is given over here. The reactants are entering and we need to solve for the flow. Catalyst is coated on the bottom and top wall between planes B and C, which are at a distance of 0.5 and 0.75 lengths, total length. This is L, so between B and C, this is 0.5, this is 0.75. So between B and C is where the catalyst is coated, and we need to understand that reaction takes place only in this region between B and C. The reactor is preheated or cooled through the top and bottom walls over the distance between planes A and B. They have not mentioned how the reactor is cooled, but in one of the questions we'll be solving for that. We need to solve for the flow in a reactor in which the following water gas shift reaction is taking place, where CO combines with H2O to form CO2 and H2. The reaction is mildly exothermic and has to be carried out in a targeted temperature range between the desired output composition. All the species are in gas phase, but the reaction is catalytic. So, in the reactor shown in figure, the catalyst is coated on the bottom wall between planes B and C, which are at a distance of 0.5 and 0.75 L respectively. We wish to use the length of the traverse between planes A and B for preheating or even cooling if the reactants are at too high temperatures. To begin, we need to find out how much conversion takes place. So we are finding out the conversion, how much of the CO is coming through the inlet gas gets converted to CO2 and to the production of H2. We want to find this out using CFD simulations, assuming steady laminar flow. Answer the following questions. So the question till now has not yet been asked. This is the problem statement that has been given to you. So maybe going through this will again understand what is going on over there. The first question related to that is, how many mass conservation equations do we need to solve? So here we know that there are four species which are CO, H2O, CO2 and H2. Therefore, we have the mass or the flow rate or the mass of these four species needs to be found out. So we need to solve four equations. And we can solve any four equations. Usually what we do is we solve three species conservation equations and one mixture continuity equation. We can't just solve just for CO and CO2 or any other way. We have to solve simultaneously four equations to get the mass flow rate of all of these species and the mixture. Which of the following is true about CFD with chemical reactions? The rate of reaction needs to be specified. The stoichiometric coefficient of the reactants reaction are sufficient to calculate the reaction rate. The rate of reaction need not be specified as it can be calculated assuming thermodynamic equilibrium, and the kinetic parameters of the reaction rate to be specified. If you specify the reaction rate, it changes with respect to position and time, so that is not the answer over here. The stoichiometric coefficients of the reaction are sufficient unless it is an elementary reaction that is very rarely occurring. If it is anything to do with a non-elementary reaction, the reaction rate cannot be determined by the stoichiometric coefficient, so that is also wrong. The rate of reaction need not be specified, but it can be calculated assuming thermodynamic equilibrium. That is also not true because the rate of reaction does vary with respect to position and time. So therefore, there is no thermodynamic equilibrium taking place over here since the reaction has to happen over the range of study, the field in which we are studying, the domain in which we are studying. And the fourth part is the kinetic parameters of the reaction rate need to be specified. That is the correct answer. We need the rate constant and the order of the reaction. Unless this is mentioned, we can't solve the governing equation using CFD simulations. Moving on to the next question, the terms related to the reaction rate would appear in which of the following equation? The mixture continuity equation is given by uh, dou rho u by dou t dou rho u by dou t plus del dot rho times u is equal to 0. The mixture momentum equation is given by du is given by the Navier-Stokes equation as du by or dou u by dou t plus del dot uu should be equal to minus 1 by rho del p plus mu by rho del square v plus g. And the mixture energy balance is given by rho cp dou t by dou t plus rho cp del dot ut should be equal to k del square t plus mu phi v plus qr. This is the term that's related to diffusion, and this is the energy or source term that is done. So we can see that in all of these three equations, there is no reaction rate that is appearing. There is no minus Ra term coming up. So or Kca power n term coming up. Therefore, none of these equations have to have a reaction rate, or reaction rate does not appear in any of these questions. Yeah. Moving on to the next question in the graded assignment, the fourth question of the graded assignment week 4. The thermal boundary conditions, where we said that between A and B we are using it for preheating or pre-cooling. So between A and B, the thermal boundary condition over the top wall can be, can it be temperature specified, can it be heat flux specified, or heat transfer coefficient specified? We have a temperature control problem. What we are doing is we are maintaining the temperature at the top of the wall to be some particular T node. This is one way to specify a reaction where we need to control or preheat the reactants that are entering, or control the temperature in the area between A and B. The second way is to provide heat or take away heat, or by cooling it. That can be done by specifying the heat flux, whether we can provide adiabatic condition for perfect insulation if the reactant is entering at the given condition, or you can say that it can be heated up, dt by dx can dt by dy can be given HA delta T, something like that, by providing an appropriate heat flux over there. Uh, yeah, it can be some function of temperature over here. If the heat transfer coefficient is specified, we are assuming there is convective heat transfer over happening over here. That does not directly determine what the temperature is at the top, or the thermal boundary condition at the top or the bottom cannot be done using the heat transfer coefficient. If just the heat transfer is given, we don't know if it's just the heat transfer is taking place, or if there is any condition over there happening. So only 1 and 2 can be done. It generally comes into picture when the whole top plane is exposed to air and or any other fluid. But in a solid wall, we don't generally have a heat transfer coefficient specified problem. So only option 1 and 2 are correct. Option 3 is wrong here. Moving on to the next question. If the reaction rate is very high, the boundary conditions for the concentration of CO, species conservation equation, at the bottom of the reactor between planes B and C. So in this region, what is the boundary condition for the bottom plate kept shown over here? Assuming that the rate of reaction is infinitely faster than the other mechanisms happening over here. So what happens here is that when the reaction takes place for CO converting to CO2, if the reaction is very high, CO is on the reactant side, CO plus H2O giving CO2 plus H2. So since CO is on the reactant side, the reaction will proceed immediately as soon as there is some CO that is in contact with the catalyst at the bottom surface. So because of which there will be the concentration of CO at the bottom can be assumed to be 0, because whenever there is a concentration of CO present, it will immediately react along with the catalyst, though it will immediately get touch the catalyst and undergo reaction to form the products. Therefore, option 1 is correct. So, will there be a concentration gradient? We cannot say that directly, because the diffusion that can happen from the points, the top wall to bottom wall, can be can exist, and it need not even be in fact constant. It can also have a gradient over It can also have a variation along the y-axis as shown here. This is the y-axis. So the correct answer is only one. The concentration at the bottom is zero. We can't say anything about the concentration gradient in space. Am I audible, Jyoti Lakshmi? Can you please confirm through a chat or a Okay, moving along, question number 6. Which of the following statements is true about the expected temperature variation along the center line of the reactor if the reactants enter at a lower than the targeted temperature? So, what happens to the variation of temperature from A to D if the reaction T in is less than the uh, targeted temperature? Let's say T set point. So what happens here is we know that the region between A to B consists of thermal heating or thermal treatment actually if you can say that, and followed by B to C having a particular reaction, and then C to D and reaction occurs. So what is the correct answer over here? What we are going to see is that since this is an exothermic reaction, what happens is that the temperature increases from A to B as the targeted the inlet temperature less than set point. So from A to B we get the temperature to be the set point over here. Let's say this is Tn. The variation of temperature along the z direction, it goes on increasing until it reaches the point B. Let this be at Tn, this will be at T set point. Now we know that as per our question, that's the whole story we had read earlier. We see that the reaction is mildly exothermic. So when the reaction is exothermic, when the reaction is exothermic, the temperature continues to increase until plane C. After C, the reaction is stopped because there is no more catalyst available, and because of that, it will remain constant. So the correct answer is D. The temperature increases up to plane C, then remains constant. Okay, moving on to the next question. The viscous dissipation term that appears in the energy conservation equation is absent in which kind of flows? Is it an inviscid flow? Is it an incompressible flow, non-Newtonian flow, or flow with shocks? That's I think made a mistake over there. It's K in the end, shocks. We have written down the viscous dissipation term in the energy conservation equation. Yeah, that is related to this mu times phi v, and we see that for the viscous when viscous term goes away if it is an inviscid flow, and inviscid definitely refers to when viscosity of the term is zero. So if the viscous dissipation term has to disappear, then it has to be an inviscid flow. This is the basic definition of the inviscid flow. An incompressible flow is when the density remains constant, and a non-Newtonian flow is when the fluid does not obey Newton's law of viscosity, where the shear strain is proportional to rate of shear stress. Sorry, shear stress is proportional to rate of shear strain, and it's not the it's in inflow switch shocks also is not possible. Okay, moving on to the next question. Which of the following is already included in the energy equation that we solved along with Navier-Stokes equations for flow with heat transfer? Again, we need to look into the energy conservation equation, where we say that rho Cp dou T by dou T is plus rho Cp del dot U T should be equal to K del square T plus mu times phi V plus QR. Again, this is the viscous dissipation term, this is the reaction energy term, this much would be the uh, convective heat transfer term, and this would be the diffusive heat transfer. So what we can see is there is no radiative heat transfer where we relate it to Stefan Boltzmann's or Stefan's law, that is sigma into T raised to 4. There is no sigma T raised to 4 relation happening here. Boiling heat transfer also does not happen here. Generally, we don't write the equation for boiling anywhere in the literature that I have seen. And all of the above require additional modeling. That's also false. It is a convective heat transfer that is given by this term. Rho Cp dou T by dou T plus rho Cp del dot Ut is the convective term, or it is also known as the advective term. Okay, moving on to the next question, we have the well posedness of an initial value problem. What does that mean? It having the guarantee of a solution, having a unique solution, having a solution that is responsive to changes in initial and boundary conditions. A well-posed solution, well-posed initial value problem has a guarantee of a solution. In fact, has only one solution according to the any problem that we are dealing with, and that one solution is extremely sensitive to the changes in the initial and boundary conditions. If the initial boundary condition is changed, then then there will be another unique solution for the new given boundary condition. So all these three make sense for a well-posed initial value problem. Please excuse me for a minute. Okay, moving on to the next question, the last question for the graded assignments in week 4. We see the boundary conditions over which the entire boundary may not be needed for what kind of a problem. A parabolic problem is parabolic, elliptic, hyperbolic, or none of the above. For most of these problems, what we have is the parabolic problem is given by dou square u by dou x square is equal to a function of the lower order terms. Okay, let me assume that I am writing a partial differential equation as a dou square f by dou x square plus b dou square f by dou x dou y plus c into dou square f by dou y square plus function of lower order terms equal to 0. Then we can say that a parabolic based on the values of b square minus 4ac, if it is equal to 0, we call that as parabolic. If it is less than 0, we call it as elliptic, and if it's greater than 0, we call that as hyperbolic. And when we solve such equations, we see that parabolic and elliptical problems are actually boundary value problems. And hyperbolic problems are generally referred to as the initial value problems. Therefore, the correct answer is C, hyperbolic. The entire domain is not required, but that's required for parabolic and elliptic. Boundary condition, one boundary condition along with one initial value condition is required for solving hyperbolic questions. Moving on to the non-graded assignments for week number 5. In this equation, d square f by dx square is evaluated at question mark. D square f by dx square is given by fi plus 1 minus 2 fi plus fi minus 1 by delta x square. Therefore, we know that this is discretized at the point x. I think the question here is not exactly correct. I think there was some error in the graded, non-graded assignments, error in practice questions, I think. So I would urge you to just check this question out before validating my, so at least validate my answer, to validate my answer. So next is a very direct theory statement. What does the Lax theorem states? It is stating whether the convergence is assured for convergence for a well-posed linear system initial value problems. Stability is assured for well-posed linear initial value problems. Consistency and stability are sufficient for the convergence of well-posed initial value problems, or none of the above. According to the Lax theorem, it states that a consistent finite difference approximation to a well-posed time-dependent linear partial differentiation is convergent if and only if it is stable. Therefore, what it states that is that stability is a necessary condition, whereas consistency and stability together constitute the sufficient condition for the convergence of a well-posed linear initial value problem. And we know that a linear well-posed system refers to a system where it has a unique solution, it has a consistent solution, and what do you say, the if the boundary conditions or the initial values are changed, then we are at a new solution. So Lax theorem deals with the consistency and stability being the sufficient condition for the convergence of a well-posed linear initial value problem, and that's coming from here. Moving on to the next question. For the expansion given by the equation, this equation to be convergent, which of the following conditions needs to be satisfied? This is a very direct linear, what do you call that? Taylor series expansion of f of x at x plus delta x. So for this equation to be convergent, what the necessary condition is that the interval that has been taken should be sufficiently small to neglect whatever corrections we are doing over the range of the system. F must be continuous to find out, and F must be differentiable. These both conditions come together and play hand in hand in order to find the differential of those points or the slope of those points at everywhere. Whereas small delta x just leads to a high accuracy or highly convergent or a quick convergence system. So all these three conditions have to be met for the system to be satisfactorily convergent. The next question, what is the value of b in equation A? And this is equation A. Since delta x here is not equal to, not given as 1, can be anything. So we have just assumed that delta x is any value. So we'll get, according to the Taylor series expansion, f of x equal to f of x plus delta x equal to f of x plus delta x by 1 factorial times df by dx plus delta x square by 2 factorial times d square f by dx square plus delta x cube by 3 factorial plus by d cube f by dx cube plus etc. So what we are seeing is the coefficient of d square f by dx square is in fact x square by 2 factorial. Therefore the answer is delta x square by 2 factorial. Unfortunately, that answer is not there in any of the answers. The only answer that is close to it is 1 by 2 factorial. Therefore, the answer is none of the above. Next, we'll move on to the graded assignments for the week that just got over, grade week 5. Week 5 was dealing with questions that are related to how you can discretize the equations and what are the different ways to get an answer from each of them. So, with respect to that, we'll start by solving the first question. In the figure, the dark thick lines indicates the boundary of the computational domain. Which of the following is a Dirichlet boundary condition on the side AB? So AB is given. And the first question is U equal to 0, which is basically known as the no slip condition. And the second one, zero stress condition, is basically tau is equal to 0, which is equal to du by dy is equal to 0. The adiabatic, if there is some kind of slip, if there is some kind of interaction between the velocity profile, velocity of the fluid and the surface over here. If there is some kind of extra moisture sticking here, then no slip condition cannot be used. We have to use zero shear stress condition. Or if this interface is defined on fluid 1 and 2 rather than this being a, if fluid this region 2 is not solid, then we won't have a slip condition. We will not have a no slip condition. We will have a zero shear stress condition instead. Therefore, in such a case, we'll get this du by dy equal to 0. The second one is adiabatic boundary. Adiabatic boundary implies that the temperature over the region dt by dy will not change. So according to the definition of a Dirichlet boundary condition, if the function value at the point at the boundary at the line AB has to be specified. Now in these three cases of no slip condition, zero shear stress condition, adiabatic boundary condition, we saw that the function value at the AB is only given for the no slip condition. The other two, the gradient of the function value or the derivative of the function value at that point is no. So therefore the correct answer is only the first one, u equal to 0. Moving to the next question. Which of the following statements is true about the computational molecule shown in the figure? And this figure is being shown here for this question. We are asking whether the central differencing of Poisson equation has this computational molecule. Central differencing of the Laplace molecule has this computational molecule. Let's focus on uh, what the Poisson equation and Laplace equation are. Let's assume that phi is a function defined on this domain, and we know that the Poisson equation is given by del square phi equal to some constant f, and the Laplace equation is given by del square phi is equal to 0. Therefore, when we write this for a two-dimensional case as given in this computational molecule, what we do is we have to write this, let us write this in terms of x and y. We'll get dou square phi by dou x square plus dou square phi by dou y square is equal to f. Similarly, here will be dou square phi by dou x square plus dou square phi by dou y square equal to 0. When we discretize this, we'll get phi I plus 1 j minus 2 phi I j plus phi I minus 1 j by delta x square plus phi I j plus 1 minus 2 phi I j plus phi I j minus 1 by delta y square should be equal to f at that point fij. And if I am to if this is equation P, equation L, let's call this as equation P and this as equation L. L will transform to phi I plus 1 j minus 2 phi I j plus phi I minus 1 j by delta x square plus phi I j plus 1 minus 2 phi I j plus phi I j minus 1 by delta y square should be equal to 0. So what we are seeing is the function value f phi I plus 1 j is this one, phi I j is this one, phi I minus 1 j is this one. Similarly, phi I j plus 1, phi I j minus 1 are these three, and fij is this one. So in both of these Poisson and Laplace equation, we are using the computational molecule as shown in this figure. And when we write the magnitude of the diagonal coefficient, or the magnitude of diagonal coefficient is greater than the sum of the magnitudes of the off diagonal coefficient. So when we write the diagonal coefficient here, we'll get that to be equal to minus 4 times phi ij, or let me read that as minus 2 times phi ij times 1 by delta x square plus 1 by delta y square plus phi I plus 1 j plus phi I minus 1 j times 1 by delta x square plus phi ij plus 1 plus phi ij minus 1 times 1 by delta y square. So we can see that the magnitude of the diagonal elements, which is 2 times 1 by delta x square plus 2 times 1 by delta y square, and here it will be 1 by delta x square plus 1 by delta. So this has a 1 by delta x square, this has a 1 by delta x square. So the coefficient, sum of the coefficient will be 2 by delta x square here. Similarly, this will also go here and here. This will be 1 by delta y square plus 1 by delta y square. And that will give you again the same value, 2 by delta x square plus 2 by delta y square. So option 3 is actually wrong. The magnitude of the diagonal coefficient is equal to the sum of is equal to the sum of magnitudes of the diagonals of the off diagonal coefficients in the same row for 99 points. This statement holds true if you are doing for an boundary points. This equation will hold true if we can do it for let me use a different color pen. If you are using for uh, a boundary point, what we can see is that this computational molecule will go to 0 provided this boundary is also given as 0. So we'll just be having to deal with these three, and basically there will be 1, 2 and 3 terms, whereas this will have minus 4 or minus 2 times delta x square plus delta y square. Please give me a minute, I'll like drink a glass of water before they receive. Okay, uh, let's resume. With respect to figure that's given over here, the discretization of which of the following ij, we may get one or more points, corner points a, b, c, d. So this is the point corresponding to I and j. So we need to find the differential or find the operator which deals with a computational molecule that has something to do like this. That is what is asked from the question. We know that as compared to the previous question, dou square u by dou x square and dou square u by dou y square, if you can see here, does not deal with a domain like that, does not deal with the computational molecule like that. We know that dou square y by dou x square will be dealing with a computational molecule in this direction. Dou square u by dou x square plus dou square u by dou y square will be computational molecule in this direction. Also, same thing goes for A and D are actually the same thing, just a minus sign is different, but still the computational molecule will remain essentially the same. When we deal with dou square u by dou x dou y, what we are essentially doing is dou by dou x of dou u by dou y, and dou u by dou y can be differentiated as dou by dou x of ui plus 1, or sorry, uij plus 1 minus uij by delta y square or delta y, and this again can be further differentiated as ui plus 1 j plus 1 minus ui minus 1 j plus 1 minus ui minus or I plus 1 j minus 1 minus u I minus 1 j plus 1 by delta x delta y. So the point I want to make here is should be j minus 1, and since there'll be a 2 over here, so there'll be a 4 over here. So the point I want to make is, since we are dealing with I plus 1 j plus 1, that is point C, I minus 1 j plus 1 will be point D, I plus 1 j minus 1 will be point A, or sorry, point B, and the final term will be both in the negative direction, I minus 1 j minus 1. So for this particular condition, we use the computational molecule, which includes the corner points A, B, C, D. Okay, moving on to the next question. In the grid that has been shown in this figure, what can we understand? That's what's basically which of the following options is correct is with respect to the grid that is shown in figure. We know that this distance is not the same. This distance is not the same as this distance, not the same as this distance, and it has progressively increasing gaps between ith and I plus first point in whatever earlier phi. Therefore, it is a non-uniform grid. Finite difference method cannot be used for this grid. That statement is wrong, as we can still define dou u by dou x as ui plus 1 minus ui by delta x. It's just that this delta x will be changing from one value to another. Finite volume method cannot be used for grid. That is also wrong, as we can define the function at the center of these two and then multiply it with the area or length or whatever it is, and then find out the expression for that correspondingly. So we are able to use finite volume method and the finite difference method for a non-uniform grid as shown here. So the only correct option is option 1. So in the next question, question number 5 of the graded week assignments for week 5, If you write a Taylor series expansion for the function at the P in the point about the point ij in figure, then the third term in the expansion is given by question mark. So what we have when we are whenever suppose this is the point P, we write it as I minus 2 and j. What happens is since j is not varying, only I is varying. So we have to assume that this distance is 2 times delta x. If because mainly because it is between the second grid point and I minus 2, it goes to I minus 2, we have to assume that that distance is in fact 2 delta x over here as written here. So we have to write down what the function is using the Taylor series expansion. So f at p is given by f at x minus, again use the Taylor series expansion. Instead of putting delta x, we put minus 2 delta x. Since this is in the negative x direction, because I minus 2 is coming, we have to use minus 2 delta x into f dash x by 1 factorial plus 2 delta x minus 2 delta x the whole square into f double dash x by 2 factorial minus 2 delta x the whole cube by 3 factorial into f triple dash x by, yeah, that's plus etc. And the question they have asked for the third term, and third term would correspond to this one. And that would be given by 4 delta x square by 2 factorial, which basically reduces down to uh, 2 delta x square. And since we are expanding about the point P, we use the function value at the point ij, or the point, or let's call this as origin O. So we have to use O everywhere. These function values are equated at f of x, not at f of p. So this finally reduces down to dou square f by dou x square at I comma j. So the correct option is option D. Okay, moving on to the next question. We have been given second order differential d square f by dx square by using this. We need to find out to what order of accuracy this is good enough. So whenever we write the second order in terms of more number of function values at ith and I plus first point. So basically what we are doing is we are writing the differential at a point based on the ith point, I plus first point, I minus 1 point, and I minus 2th point. So we'll be considering the function values over these entire region, and it will become more and more accurate when we solve it. That's the reason behind doing such an analysis. So when we try to solve this problem, what we are doing is we write this d square f by dx square as this is known as the method of undetermined coefficients. the reason this name is kept because we just write down the expansion of d square f by dx square as a times fi plus 2 plus b times fi plus 1 plus c times fi plus d times fi minus 1 plus e times fi minus 2. And we expand at, we use the Taylor series at each of these points to get the corresponding equations. So basically what we are doing is, since there are 5 unknowns, we expand this up to the 5 terms. So we write this as fi plus 2 can be written as f at fi plus 2 delta x by 1 factorial times fi dash plus 4 delta x square by 2 factorial times fi double dash plus 8 delta x cube by 3 factorial times f triple dash plus 16 delta x raised to 4 by 4 factorial times f quadruple dash plus higher order terms. But since there are only 5 coefficients, we write down up to 5 terms, 1, 2, 3, 4, 5. And we add on similarly, so fb would be delta x by 1 factorial times fi dash plus delta x square by 2 factorial fi double dash plus delta x cube by 3 factorial fi triple dash plus uh, delta x raised to 4 by 4 factorial fi quadruple dash. So what we can see here is that up to delta x raised to 4, we have taken into account for all of these equations. There is a similar equation for c, d and e. Up to delta x raised to 4 we have taken up. So therefore the order of accuracy is actually greater than delta x raised to 4. That means it will be of the order of delta x raised to 5. So the correct answer is actually none of the above. A very high order of accuracy is obtained when we do in this method. I'll just write down what is there for c into f of I plus d into fi minus delta x fi dash by 1 factorial plus delta x square fi double dash by 2 factorial plus minus delta x cube fi triple dash by 3 factorial plus delta x raised to 4 by 4 factorial fi quadruple dash plus e times fi minus 2 delta x into fi dash by 1 factorial plus 4 delta x square fi double dash by 2 factorial minus 8 delta x cube fi triple dash by 3 factorial plus 16 delta x raised to 4 by 4 factorial fi quadruple dash. So we see that all of these equations have delta x raised to 4 in them. Up to delta x raised to 4 we have added it to the accuracy. And so the order of accuracy is delta x raised to 4. And sorry, delta x raised to 5. We are neglecting the order of delta x raised to 5 over in each term. Now the next question is a numerical problem based on what we just have solved right now. So what they have asked is d cube f by dx cube is written in terms of fi plus 4, I plus 3, I plus 2, I plus 1 and fi. So basically what we have is a function that is going on like this. So suppose this is basically I. We have used I plus 1, I plus 2, I plus 3 and I plus 4 to find out the third derivative d cube f by dx cube over here. We can get this by again the same method of variation of parameters. We can get this by d cube f by dx cube should be equal to minus 3. Let's call the undetermined coefficients as a into fi plus 4 plus b into fi plus 3 plus c into fi plus 2 plus d into f of I plus e into f of I. 4, 3, 2, this has to be fi plus 1 and e into f of I. We expand f in each of these terms. So we can write this as a into f of I plus up to, we need again up to 5 terms. Since there are 5 unknowns, 1, 2, 3, 4, 5, we have spanned up to 5 terms. fi, and we use the second term, and since it's an I plus 4, we'll get 4 times delta x by 1 factorial times fi dash plus 16 times 2 factorial into delta x square times fi double dash plus 4 cubed will be 64 times delta x cubed by 3 factorial times fi triple dash plus 4 raised to 4, that means 2 raised to 8 will be 256 by 4 factorial times fi quadruple dash. Similarly, we write for b as fi plus 3 delta x by 1 factorial times fi dash plus 9 delta x square by 2 factorial fi double dash plus 27 delta x cube by 3 factorial fi triple dash plus 3 raised to 4, that is 81. There will be a delta x raised to 4. Delta x raised to 4 by 4 factorial times fi quadruple dash plus c into f of I plus 2 delta x by 1 factorial fi dash plus 4 delta x square by 2 factorial into fi double dash plus 8 delta x cube by 3 factorial into fi triple dash plus 16 by 4 factorial into delta x cube times fi quadruple dash plus d times fi plus delta x by 1 factorial. This would be the general easiest expansion of the Taylor series. Delta x square by 2 factorial fi double dash plus delta x cube by 3 factorial fi triple dash plus delta x raised to 4 by 4 factorial fi quadruple dash and e times the function value. Since this is evaluated at fi plus fi, you don't have to Taylor series expand this. Now what we do is on the left side we know that it is fi triple dash. Since it's given as d cube f by dx cube is given, we have to find out fi triple dash. We have given fi triple dash over here. Now we evaluate the coefficients with respect to the function value on the left side. Here we know that the function value fi has 0 coefficients over here. So we can write that as a into fi plus what I am planning to tell you is I can write a into fi plus b into fi plus c into fi plus d into fi and d into fi and equate that to 0 since there is no term on the left side. So I can write the term as a plus b plus c plus d plus e to be equal to 0, and this I am calling it as equation number 1. And then from the second term I'll get delta x by 1 factorial times fi dash. That is common for everything. And this has 0 times delta x by 1 factorial fi dash. So I can write that as the following: 4 times a plus 3 times b plus 2 times c plus d should be equal to 0. Basically, I'm taking the coefficients of a for fi dash, for b and fi dash, c and fi dash, and e and fi dash. So that comes out to 4 times a plus 3 times b plus 2 times c plus 1 time e plus 0 times e, and multiply it with the common elements is delta x fi dash by 1 factorial, which goes out to 0. And I'm calling that as equation 2. Now I take the third term where I have the squares of the function here, 16, 9, 4, 1, and again 0 here. So I'm going to write that down as well. 16a plus 9b plus 4c plus d is equal to 0. This would be equation number 3. Again, moving on for fi triple dash, I'll have 64, 27, 8, and 1, and obviously 0 here. So it will be 64a plus 27b plus 8c plus d, and we can't equate that to 0 because we are finding for fi triple dash on the left side, and we have equated that for fi triple dash over here. Therefore, we have to equate that to 1. And similarly, we do it for the last element also. We'll be getting it as 256a plus 81b plus 16c plus d should be equal to 0. And we can solve this. We have 5 equations and 5 unknowns. You can solve the system of 5 equations and 5 unknowns and finally get the answer for a, b, c, and d to be, we'll get a to be minus 3, we'll get b to be 14, we'll get c to be minus 24, we'll get d, we'll come back to d, we'll get e to be minus 5. When we solve it, we'll get e as 18. Therefore, the correct answer is 18 over here. When we solve this, we'll get the answer to be in that. We have to just find out a, b, c, d, e and resubstitute it in this equation. Sorry, we'll get a little bit different answer. I think we'll get this as, we'll not be getting this to be the answer. We'll be getting the coefficient, or we'll just, you may have to calculate the value over here. We'll get the final, or let's just call it as d cube f by dx cube would be equal to minus 3 fi plus 4 plus 24, if I remember, 14, sorry, 14 fi plus 3 plus minus 24 fi plus 2 plus 18 fi plus 1 minus 5 fi. Divided by 2 times delta x squared. Therefore, the correct answer is actually 18. When you solve it, you'll be able to get a very direct, straightforward substitution that's happening over here. I'll just keep it like this for a minute so that if you need to write it down or something, I'll let you do it. Okay, moving on to question number 8, which is basically a theory question. Convergence condition is about the equivalence between which of this? The exact numerical solution of the PDE, exact solution and numerical solution of the discretized equation, exact partial differential equation and the discretized equation, and none of the above. Basically, what it's meant by the exact solution of partial differential equation is the analytical method, and numerical solution refers to the finite difference or whatever the CFD method we have used over here. The exact solution and numerical solution of the discretized equation refers to the technique we are using. Suppose we are using Gauss-Seidel or Gauss-Jacobi iteration method, it refers to that over here. The exact partial differential equation and the discretized equation is basically straightforward. Whether the analytical solution from the partial differential equation or the actual solution while solving the discretized equation is the matching happening. So the convergence condition is basically defined for the exact and the numerical solution of the partial differential equation. This is a theory question that just needs to be known in general. There's nothing analytical or thought to be done over here. So therefore the convergence criteria or convergence condition is between the exact solution of the PDE and the numerical solution that we do by CFD. Answer is option A over here. Moving on, which of the statements is true about differencing schemes? Inconsistent schemes cannot be stable. For stable schemes, inconsistency does not matter. An inconsistent scheme will not yield the correct solution. A stable scheme will lead to converged solution within truncation errors. So, by definition, what do you mean by this consistent and inconsistent scheme, and what is meant by stability and instability or unstable scheme? So, basically, I'll write this down. Consistent, or let me just write that as consistency, refers to a quantitative measure of extent to which the exact solution satisfies the discretized solution. Whereas stability is a quantitative measure of well-posedness of the discrete problem. Therefore, what we can analyze from this is that the stability deals with whether the uh, stability deals with the measure of the well-posedness of the system, and the quantity deals whether the exact solution satisfies the discretized solution. So what can be said about these things? An inconsistent schemes cannot be stable. That is not true. Even if a system is consistent, its stability can be questioned by the well-posedness of the discrete solution. For stable schemes, inconsistency does not matter. If the scheme is stable, then If it is inconsistent, then we won't be able to get a solution. So that is also wrong. This is wrong. This is wrong. An inconsistent scheme will not yield the correct solution. That statement is correct because we know that the measure of this exact solution matches the discretized solution is given by the consistency of the scheme. So therefore, an inconsistent scheme will not yield the correct solution is correct. And a stable scheme will lead to a converged solution within truncation errors. That we can't say. That we have to base it on the convergence criteria. So we can only say that an inconsistent scheme will not yield the correct solution is the correct statement that has been given among the options that has been shown here. Please excuse me for a minute. Okay, moving on to the last question for the day. A grid independent solution is expected to agree with analytical solution of the PDE, exact solution of the discretized equation. A grid independent solution is when uh, the solution is not exactly dependent on the grid. Regardless of how the grid is, we are getting a solution. So we are expecting that to agree with the analytical solution of the partial differential equation because it's not independent of how we have discretized the domain or how the interval has been calculated, but it should not match with the exact solution of the discretized equation is what I would answer. Some of my video has seemed to be frozen, or I don't know if I am visually seeing this properly, but I don't know. Okay, that's it for the class today. I don't have any more questions to discuss with you. If anyone has any questions, please feel to ask in the chat box or unmute and speak. I'll be there until half an hour more. Okay, I sincerely thank you for your time and attention, and I hope it has been a pleasure talking to you. And I hope to see you next week then. Thank you.